Road freight traditionally operates within strict, static boundaries. To prevent vehicles from overwhelming infrastructure, lawmakers have historically capped truck lengths at exact dimensions, usually around 25 meters across much of Europe. But the demand for greater payload density is straining those rigid limits. On April 15, 2025, Sweden implemented an update to Regulation TSFS 2025-17. This legislation permits specific vehicle combinations to stretch up to 34.5 meters on designated road networks. This extension is possible because the regulatory framework shifted to what are known as performance-based standards, or PBS. Instead of merely drawing a static box and requiring a truck to fit inside it, PBS measures exactly how the vehicle actually behaves in motion. If the combination meets strict dynamic safety thresholds during cornering, braking, and evasive maneuvers, it is allowed on the road, regardless of its total footprint. This engineering-first approach clears the way for 5 newly approved multi-articulated layouts. Operators can now deploy the A-double, the AB-double, the B-double, the C-double, and the Nordic Combination. The Nordic Combination, for instance, uses a 12-meter rigid truck, a dolly, and a standard 13.65-meter semi-trailer. By discarding arbitrary length caps, engineers can scale up payload capacity, filling the available space right up to the mathematical edge of physical stability. Pushing a mass of steel and cargo cast 25 meters introduces severe high-speed instabilities. The most critical metric engineers must solve is rearward amplification. This occurs when the vehicle executes a sudden high-speed maneuver, like a lane change to avoid an obstacle. A minor steering input creates a lateral acceleration force at the tractor. Because the combination features multiple articulation points, that kinetic energy transfers backward, multiplying at each pivot like a cracking whip, creating a massive lateral force on the rearmost trailer. To prevent the back of the combination from swinging out of control, Regulation TSFS 2025-17 mandates the use of electronic braking systems featuring automatic adjustment. These electronic systems provide precise yaw damping. By independently pulsing the brakes on specific axles in milliseconds, the system bleeds off kinetic energy, interrupting the oscillation before it destabilizes the rear. The second major hurdle in the PBS framework is the steady-state rollover threshold. During a long, sweeping highway curve, lateral acceleration pushes the trailer's center of gravity outward. If that outward force vector extends past the outer edge of the tire track width, the trailer tips. Engineers must calculate the exact height and weight limits to ensure the tires stay planted. Managing these forces places extreme shear stress on the mechanical linkages tying the units together. The hitch connecting the dolly in a Nordic Combination, for instance, must be rated for a dynamic load capacity of at least 130 kilonewtons. Taming rearward amplification, maximizing yaw damping, and clearing the rollover threshold are the mandatory engineering requirements. Passing these tests is the only way a transport operator is permitted to operate these high-capacity configurations on public roads. While highway stability is a matter of managing kinetic energy, urban maneuverability introduces a different physics problem: drag and tracking. Navigating tight intersections with 34 meters of trailer requires specific trailer axles to feature active or passive steering at speeds under 30 kilometers per hour. This allows the rear units to cleanly follow the tractor's path, instead of dragging their tires laterally across the asphalt. But hauling extra axles creates a severe efficiency penalty. When a combination drives back empty, the gears and bearings inside the driven axles continue to generate heavy internal friction. To eliminate this parasitic loss, physically separates the second driven axle from the powertrain. Pneumatic suspension then lifts the entire axle 70 millimeters off the ground. With the tires in the air, the heavy gear rotation inside the housing is instantly halted. Removing that mechanical drag reduces fuel consumption by up to 6%. Lifting the rear tandem axle also shortens the effective wheelbase, giving the empty truck a tighter turning radius while completely eliminating wear on those tires. Without these highly targeted, component-level mechanical solutions, the theoretical efficiency gains of moving larger payloads would be entirely consumed by the physical friction required to move the vehicle itself. With the dynamic stabilized and mechanical friction minimized, the final variable for scaling these 34.5-meter combinations is the energy source, replacing diesel powertrains with massive battery electric systems. The primary industry constraint regarding electrification is the severe carbon debt incurred up front. Mining the materials and manufacturing the dense battery packs required for a 40-ton commercial vehicle requires massive industrial energy. This chart shows life cycle assessment data comparing a 40-ton battery electric truck against a diesel equivalent over 1 million kilometers. At the y-intercept, the initial carbon debt is steep. Producing the EV generates 52 tons of CO2 equivalent, double the 25 tons from manufacturing the diesel. But on the road, a diesel engine burns fuel continuously, driving emissions sharply upward. The EV's emissions accumulate at a near flat rate. With low-carbon electricity, the lines intersect, paying off the EV's debt in 37,000 kilometers, or 59,000 kilometers on the standard European grid. Over the 1 million kilometer lifespan of the vehicle, the battery electric system eliminates up to 90% of total lifetime emissions compared to diesel. The empirical data demonstrates that the heavy upfront carbon cost of battery manufacturing is statistically insignificant when measured against the operational lifespan of commercial freight. Theoretical modeling is now being tested through the physical deployment of 34-meter electric fleets. Commercial operators like Joula Logistics are moving past the design phase and actively constructing the infrastructure to operate zero-emission, high-capacity networks. To fuel these combinations, they built an energy generation point directly into their distribution center, anchored by an 8-megawatt solar array. The array and grid feed a 2-megawatt stationary battery. From this buffer, energy distributes through 350 kilowatt nodes directly into the 34-meter trucks. By generating and storing power on site, the transport operation physically disconnects from external fossil fuel supply chains. They insulate their freight network from global diesel price volatility by producing their own fuel. Moving the maximum allowable tonnage inside a 34.5-meter limit, powered entirely by a closed-loop solar array, achieves a specific goal: physically separating a fleet's ton-kilometer output from its carbon emissions. The integration of these three pillars, dynamics, mechanics, and electrification, provides the framework for a sustainable freight system. By aligning performance-based standards with renewable energy loops, the industry has established a scalable blueprint for the future of logistics.